Hello everyone. Today we'll discuss about octave band analysis. Okay, so first of all we have to know about tone. What do you mean by tone? Tone means the sound sensation in human ear. Okay, so there are two types of tone. One is pure tone, one is complex tone. Pure tone is equal to one single frequency. So whatever type of tone is generated from a source, if it is having only one frequency, then it will be known as a pure tone. As an example, you can see you can say that some kind of striking of some kind of vibrating object like a tuning fork or a string of a guitar, whatever type of sound is generated, that will be an example of pure tone or single frequency tone. Now complex tone is a combination of more than two tones. Okay, so there will be 2 3 4 5 numbers of tone. As an example, speech, whatever I am talking, that is an example of complex tone. Music from any kind of sources or roadside noises, all are comprising of more than two numbers of frequencies. That's why they are known as complex tone. Also in the picture you can see just the division of tone into pure and complex tone and their examples. Now come to fundamental tone and overtone. Say for example, you are analyzing a complex tone. Complex tone means there will be presence of more than two number of frequencies. Let us have an example. Our case, say in the picture you can see complex tone comprising of 8 to 10 numbers of frequencies like 50, 75, 80, 100, 160, 250, 325, 450, 535, 750. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 number of frequencies are present in this complex tone. So the lowest frequency present in this series or lowest frequency present in the complex tone will be known as the fundamental tone. Okay, you have to find the lowest frequency present in the tone, in the complex tone, that will be your fundamental tone, and the remaining portion apart from the fundamental tone, that is from 75 to 750, in our case it will be known as overtone, or sometimes it is known as integral frequency, sometimes it is also known as partial tones or partial frequencies. So a complex tone will be comprising of fundamental tone plus overtone. Okay, now in this example, or sometimes you will find that some frequencies will have a suitable relation between them. Say for example, in this case, in our example, we can see that the red marked frequencies, that is the 50, 100, 250, 450, 750, a suitable relationship is there between this 1, 2, 3, 4, 5, 5 numbers of frequencies. Now if these frequencies are the integer multiplier, then all of them will be called as a harmonics. Why? If the frequencies are a result of integer multiplier of the fundamental tone, then comprising of all these tones will be known as harmonics. Not the all tones, only the multiplied values are the harmonics. Say for example, in our case 50 multiplied by 2 equal to 100. Similarly 50 multiplied by 5 equal to 250. Similarly 50 multiplied by 9 equal to 450, and 50 multiplied by 15 will give you 750. So comprising of 50, 100, 250, 450 and 750, all of this will be known as harmonics, including the 50, because from 50, that is the fundamental, from the fundamental tone, you are getting the 100, 250, 450, 750 values. So comprising of these 5 tones, 1, 2, 3, 4, 5, will be known as harmonics, including the 50. Okay, now come to octave. What do you mean by octave? If a frequency is double of the another frequency, then these two frequency will be interrelated, and that relation will be known as octave. If one frequency is double of the another, then the relation between them is known as octave. Okay, say for example, you have a complex tone and the frequencies present in that complex tone as given in the picture also. There is 25, 50, 75, 100, 150, 200, 350, 400, 500, 800, 950. You can see. So first of all, what is the fundamental tone? There is 25. So fundamental tone is 25. Then the remaining part from the 50 to 950, it will be known as overtone, integral frequency or partial frequency. Now you can see there are some relation between the red marked frequencies 25, 50, 100, 200, 400, 800, but all the frequencies are related to 25, because 50 you can get by 25 into 2, 25 into 3 will give you 75, 25 into 4 will give you 100. So all the frequencies are result of integer multiplication with 25. So all of these frequencies will comprise or will be known as harmonics. But some of the frequencies, that is 25, 50, 100, 200, they have a specific relation. 25 multiplied by 2 will give you 50, 50 multiplied by 2 will give you 100. Similarly 100 into 2, 200, 200 into 2, 400, and 400 into 2, 800. So comprising of this 25, 50, 100, 200, 400, 800 is giving you a suitable relationship. Now what was the definition of an octave? If a frequency is double of the another frequency, then these two frequencies will be known as octave. So 25 and 50, 50 is the double of 25, so 25 and 50 will be known as octave. Similarly 50 and 100 octave, 100 and 200 octave, 200 and 400 octave, 400 and 800 octave. And comprising of this 25, 50, 100, 200, 400, 800 will be known as the octave band. Okay, octave will be two frequency having relation of x2 or frequency 2 equal to 2 into frequency 1, but comprising of this double frequencies will give you the octave band. Okay, now come to next, octave band. In bracket you can see 1 by 1 letter, octave band central frequency. So why this generally octave band is known as 1 by 1 octave band? Why it is called as 1 by 1? I will come to it later. First of all, just learn what do you mean by octave band central frequency. Now human ear is sensitive for the case of frequencies, frequency range between 20 Hz to 20,000 Hz. Now you can say one sound is generated, one noise is generated from a source, a machine, or from any kind of vibrating object. Then whatever sound is produced, to analyze the sound, if you just dissociate the sound or the noise into different frequencies, then you can get there are more number of too many number of frequencies present in that noise. By this process, if you go for the analysis, then it is very difficult. That's why we are instructed, or you can say there are some standard or reference frequencies already given by the standard Indian standard, that we need to take this standard frequency to analyze any kind of noise. So basically there are 10 number of standard frequencies or reference frequencies given to analyze any kind of noise having frequency range between 20 to 20,000 Hz, 20 Hz to 20,000 Hz. In this range, any kind of noise generated can be analyzed using this 10 number of frequencies. These frequencies are given in the picture, handwritten. You can see 31.5 Hz, then 63, 125, 250, 500, 1000, up to 16,000. Okay, so also you can see in this 10 number of frequency band, that is the each and every frequency is double of the previous one. As an example, 63 is double of 31.5. Similarly 125 is almost double. To get an you can say round of figure, it is written here as 125, not 126. 31.5 multiplied by 2 will give you 63. Similarly 63 into 2 will give you almost 125. Similarly 125 into 2, 250, 250 into 2, 500. So all the frequencies are the double of the previous one. That means they are octave, and also the comprising of this 10 number of octaves is known as octave band, and these octave band frequencies are the central frequency of octave band. Okay, now come to the calculation of band number. Band number can be calculated by this formula, that is 10 log 10 frequency. Any frequency, that frequency can be taken from this octave band. So for the first band number, that is band number 1, we have to take the first frequency, it is 31.5. so for band number 1, 10 log 10 31.5 give you almost 15. Similarly for band number 2, you can directly calculate 10 log 10, that is frequency 2 means 63, it will give you 18. By this process you can calculate each and every band number for this all 10 octave band central frequency. The short form is OBCF, octave band central frequency, from 31.5 to 16,000. So come to next picture. In this picture there are some calculation. So first of all, think about one single octave band central frequency starting from 31.5. It is central frequency. So say for example, this central frequency is having two hand like us, right hand and left hand. Okay, say for example, the left hand is the lower frequency and right hand is the upper frequency, or lower limit and upper limit, lower band or upper band. Whatever octave band from the octave band central frequency list we are getting, that is the central frequency. So this central frequency will have a lower band and upper band. Whenever you can calculate the lower band or upper band including the central frequency, it will give you a band width. Width means the width of any section, width of band, the range of the band from lower to upper including the central frequency. Now how to calculate the lower band and upper band? Lower band formula is frequency minus 0.3 multiplied by the frequency, ultimately giving you the 0.7 multiplied by frequency. Similarly for the upper band, f plus 0.4 into f, that is frequency plus 0.4 into frequency, will give you 1.4 of the frequency. So for an example, if we take the first frequency of the octave band central frequency as 31.5, then for the 31.5 lower band you can calculate by multiplying it with 0.7, it will give you 22. Similarly upper band 31.5 multiplied by 1.4, it will give you 44. Now come to the next frequency. Next frequency was 63. You can check from the list. First is 31.5. Also you can just multiply 31.5 with 2, that is I have also written here the frequency 2 equal to 2 into frequency 1 equal to 63. So for the second octave band central frequency as 63, we can calculate also the lower band and upper band. Similarly you will get the lower band as 44 and the upper band as 88. From these two calculation, whatever you can see that the upper band of the previous central frequency is equal to lower band of the next frequency. Why? You can see 44 is the value in case of upper band calculated for 31.5 and 44 is the value in case of lower band calculated for 63. So the upper band of central frequency will be equal to lower band of the next frequency or next octave frequency. Similarly by this process you can calculate easily the range of the or the bandwidth, lower band or upper band, for each and every octave. For 31.5 it is 22 and 44. Similarly for 63 it is 44 and 88. Similarly for 125 it is 88 and 175. Okay, almost 88 and 175. To get an round of figure, it is written as 175 instead of 176. Okay, I have just indicated with a red arrow, you can see. So you can also calculate on your own using the octave band central frequency, band number and band width. And just you can create also this kind of table. Octave band central frequency, that is OBCF, band number, you can use the formula 10 log 10 frequency, and bandwidth, lower band and upper band. Okay, by this process you can create this bandwidth, band number for different type of octave band central frequency. Now, necessity of octave band. First necessity is the, or first requirement is the octave criteria gives an opportunity to logically select some specific frequencies from a noise. Whenever a noise will be analyzed by you, then you do not require a huge number of sound or huge number of frequency. You require a suitable frequency. Using that frequency you will analyze it. This kind of band will automatically filter and give you the required or suitable type of frequency for the analysis. Second one is the logarithm of the octave frequencies are separated by equal distance. Logarithm of octave frequency means log 10 of octave frequency. Also, logarithm of octave frequency, that is the band number. What here it is written that the frequency logarithm of octave frequencies are separated by equal distance. You can see the band number. For the first case the band number is 15. For 31.5 it is 15. For next one 63 it is 18. For next one 125 it is 21. For next one 24, then 27, then 30, 33, 36, 39, 42. All these values are band number. Now these band number are separated by a suitable distance of 3. 15 to 18 3, 18 to 21 3, 21 to 24 3. So all the band number, that is the logarithmic value of octave frequencies, octave central frequencies, will give you a series maintaining a suitable spacing of 3. From this table, whatever you can say that octave frequencies are lying in a GP series, 31.5, 63, 125, 250, all are these values are lying in a GP series, and the band number, that is 15, 18, 21, 24, all are lying in a AP series. GP series means geometric progression, AP series means arithmetic progression. So octave band central frequencies lie in a GP series, band numbers are lying in a AP series. That is here written in the number 2 necessity as logarithm of octave frequencies are separated by equal distance. Next, the third necessity is that central frequencies provide common platform for material testing and assess the acoustical data. Whenever one acoustic situation is there, that you have to analyze the acoustic data, acoustic sound, and also the sound or noise generated from a machine, you can directly use these central frequencies or octave band central frequencies to filter out suitable number of frequencies for your analysis purpose. These are the analysis of a octave band and the requirement and how to calculate different values and requirement, necessity, needs of the octave band. Okay, now come to the section of 1/3 octave band. In the previous case it was mentioned as 1/1 octave band. Now it is 1/3 octave band. 1/3 octave band can be produced from this 1/1 octave band and used when more number of reference frequencies are required to analyze more complex noise. In case of 1/1 octave band, we have standard number of frequencies of 10, from 31.5 to 16,000. Only 10 data are available for the analysis. But for some other analysis purpose, for some more accurate result, we need more number of standard value. That's why this 1/3 octave band has been generated by standards. Okay, now 1/3 octave band you can also generate. What is the process? We will discuss. So first of all, make a table, that is for 31.5 octave band central frequency, you have that band number as 15 written in the black color. Similarly for 63, the band number is 18. can be calculated by the formula 10 log 10 63. Okay, now between 15 and 18, that is there are two numbers is present, 16 and 17. Okay, just fill the number 16 17 and also one number previous of 15 and one number next to 18, that is from 14. Let us just fill up all the gaps from 14 to 19. 14 15 was standard, then 16 17 you are adding, 18 was standard, then 19 you are adding. So whatever value you are getting as a series, 14 15 16 17 18 19. Now for 15 you have the octave band central frequency as 31.5. Similarly for 18 you have 63. But for 14 16 17 and 19, what will be the central frequency? You can just calculate, or you can make a back calculation using the same formula. Now for using the same formula, all these values, that is 14 16 17 18, all will be divided by 10. First of all it will be divided by 10, then you can take the anti-log. Anti-log means 10 to the power of the number. That is, first of all, say for example 14 divided by 10 will give you 1.4. Anti-log of 1.4 means 10 to the power 1.4. You can calculate, or you can just put formula in Excel sheet. Automatically you will get the value of 25. Now for corresponding to 16, anti-log of 16 divided by 10, that means anti-log of 1.6 will give you 40. Similarly for 17, anti-log of 1.7 will give you 50. Similarly for 19, anti-log of 1.5 1.9 will give you 80. So basically, after filling the gaps in the standard band number by 14 16 17 19, we are getting the original central frequency corresponding to each and every band number, whatever you have filled or I have filled, from 25 to 80. 25 then standard 31.5, then 40 50, then standard 63, then 80. Whatever this data has been generated, this series, that is from 25 to 80, this is known as the 1/3 octave band. This series is generated or already generated to make more number of standard frequency, more number of standard octave band central frequency to be used for the analysis purpose of a complex noise for more accuracy. So similarly, we have filled only for 31.5 and 63. If you fill all the remaining gaps between 15 18, then 21 24, you can see the picture in the next picture, that is from 31.5 to 63 125 250. Band number was standard 15 18 21 24 27. Ultimate band number is 42. So one band number before the first one and one band number after the last one, that is from 14 to 43 you are filling. You can also calculate by on your own. So from this 14 to 43, you can take the anti-log of this band number divided by 10. Automatically you will get the original octave band central frequencies. From 25 to, it is coming as 20,000. So if a noise is generated and you are analyzing in the range of 20 Hz to 20,000 Hz more accurately, then you require more standard number of frequencies. That's why this octave 1/3 octave band has been generated using the 1/1 octave band, and the 1/3 octave band series is from 25 to 20,000, including all the given octave band, that is from 25, then 31.5, then 40 50 63, then 80 100 125, then 160 200 250, then 315 400, like this up to 20,000. Okay, so basically from the calculation also you can just count, you will get 30 number of 1/3 octave band central frequencies. 30 number of 1/3 central band or central octave band central frequencies from 25 to 20,000 Hz. Similarly, 1/1 octave band was given in standard as 10 numbers from 31.5 to 16,000. Both the octave bands 1/1 also 1/3 are required for the analysis purpose or each and every complex noise. Okay, these are the basics of 1/1 octave band already we discussed, and this is the basic of 1/3 octave band. Also the next picture just show you the different type of sound which lies in which zone. So basically you can see in the x-axis the data given here is 20 to 16,000 hertz. All are the frequencies. Just write down the frequency in hertz. Okay, from 20 to 16,000. So first of all, from 20 to 250 it is lower range. Just write down this kind of note. From 20 hertz to 250 250 it is lower range. From 250 to 2000 it is mild range or medium range. 250 to 2000, and from 2000 to 16,000 it is high range. Okay, so there are three range: 20 to 250 low, 250 to 2000 mid or mild, 2000 to 16,000 or sometimes 20,000 it is high. So now first of all, the hearing range for young like you can hear there is a hearing range. It's generally between 31.5 to 16,000. Similarly, the hearing range for old, that is having older age, that is from 31.5 to 4,000. Whatever frequency is given here, that is from 31.5. Generally it is taken as 30 from 31.5 to the upper limit, not from the 21. So 31.5 hertz to 4,000 hertz, it is the range for hearing range for old. Similarly, male voice will lie in the range between 125 to 4,000 hertz. Similarly, female voice will lie in the range of 250 to 8,000. And musical instrument comprises all the range, that is from 31.5 hertz to ultimately 10,000 or sometimes it is 16,000 hertz. Just for your information, this data has been given here. So this is all about the octave band analysis and different type of measurements and the analysis process. Okay.